Welcome to the fifth lecture of quantum field theory. Today we're going to continue our study of the quantum scalar field. So in the last lecture we wrote down our first candidate quantum theory that could be a quantum field theory. So we wrote it down, right? We didn't, and we solved it. It's true that we even solved it. So this is the model we ended up studying in the last lecture. Let me just check I've got all the factors of a half correct. Yeah. So we wrote down this particular model in the previous lecture, subject to, why is it a quantum model? Because, well, these things are meant to be operators of some sort. And as operators, they obey the following equal time commutation relations. So the argument here, we're working it on an equal time slice, which we can set to be t as 0 for the moment. So this is just the spatial coordinates here. And these things here are meant to be some kind of operator. I say the word some kind because they're actually a distribution valued operator if we want to be pedantic. But there's no harm in studying the scalar field in just thinking of these as operators, some kind of improper operator on a Hilbert space. But be warned, it's not really an honest operator, this thing here. It's only an honest operator when you smear it against something. But I won't dwell too much on that subtlety because in the end we can work around it. We wrote this down by analogy, right? Remember what I said about quantization? Quantization is an educated guess. This was our educated guess at a quantum Hamiltonian with these observables here. And then we managed to go a little bit further than just writing down a Hamiltonian. We actually managed to solve this Hamiltonian. And the trick was to remember that when you have a model like this, you can think of it as just a bunch of harmonic oscillators, and then to use what we know about solving systems of harmonic oscillators to solve essentially, again, by analogy, this model. And we came up with the following solution. And let me again check that all the factors of a half are correct here. And pi's, of course, you must not forget pi. And these operators here, these ladder operators, obey the canonical commutation relations. Namely those. So that's great, right? Aren't we done? We've written down a Hamiltonian, we've diagonalized it. Well, we're really not that done at all. The difficulty here, oh, again, I forgot 2 pi's. Sorry about this. It's important to keep the 2 pi's in there, otherwise you'll get 2 pi's to the power 9 or something horrible. Okay, so are we done? The answer is we're not done, not by a long way. Now, when you study the quantum harmonic oscillator in non-relativistic quantum mechanics, at this stage you were kind of done, right? But here we're not. And the reason, I'll write out what omega p is. The reason we're not finished with our discussion of the scalar quantum field is that we actually want a bit more than just that we diagonalize it. We want to call this a relativistic quantum field theory. Is it a relativistic quantum field theory? Yep.
Did you miss a dagger over the A?
I almost certainly missed a dagger over the A, thank you. Yeah. Now it makes much more sense. Thank you. Have I missed any other daggers? Looks okay, I think. Right, we may have solved HKG, but is it a relativistic quantum field theory? Have we succeeded in our goal of building our first relativistic quantum field theory? And the answer is, well, not yet. There's much that can go wrong still. To be able to say we've built a relativistic quantum field theory, we need a projective unitary representation of the Poincare group. And until we've produced this representation, we don't get to call this thing a relativistic quantum field theory. What we've built so far is a one-parameter subgroup of the Poincare group. So at best, we've managed to build a one-parameter subgroup of the Poincare group, or representation of this one-parameter subgroup of the Poincare group, namely translating in time. That's this very simple one-parameter subgroup. That's all we've managed to establish so far. I mean, insofar as we've got this operator here, we can exponentiate it and translate ourselves in time backwards and forwards. All right, well, that's actually a bit disappointing because any quantum system gives you a representation of the one-dimensional subgroup of the Poincare group given by time translations. So it's not actually relativistic at this point at all. What we need to do is find out how to represent all the possible Lorentz and Poincaré transformations that we might want to do. And that's the goal that we're going to set to this lecture. In fact, it's going to take us quite a few lectures to really achieve this goal. In the coming lectures, I'm just going to argue that it's plausible we've got a representation of the Poincaré group, and only later will we actually build a unitary representation of all the Lorentz transformations and Poincaré transformations. That's the final goal before we can really agree that we've managed to build a relativistic quantum field theory. And the way we're going to achieve this goal is by more guessing. See, really the only general purpose method to doing this is just to guess. So we're going to put on lots of hats, and only then could we hope that we built a relativistic quantum field theory but that only happens if those conserved charges, the hatted versions, obey the right algebra. So that's what we're going to do, right? You take your conserved charge and you just put a hat on it. It's very simple. We know we have lots of conserved charges to play with. We have 10 for the Poincaré group, if I remember correctly. Can that be? 4, 7, 9, 10, no, 14. We have all the Lorentz transformations. And then we have the 4 translations in time and space. We're not going to do the Lorentz part today. We're just going to still do the translation part. We're going to focus on the momentum. The generators of translations. I think it's T naught J. I never quite remember. Yes, indeed. Good. We want to build all these operators. We want to build quantum versions of all these conserved charges coming from Noether's theorem, and then we just hope, you cross your fingers and you look to the heavens and you check, do these things here obey the right algebra? And if so, then you declare victory. And if not, then it's back to the drawing board. Your first guess failed. And you've got to come up with a way of dealing with that failure when it happens. Now, luckily in this course, all the free field theories that we talk about will automatically the hat procedure succeeds. There are basically no ambiguities. We can just write them down and life is good to us. But as soon as you have interacting quantum field theories, everything can go wrong. This guess here fails more often than not, and then you're reduced to other arguments, maybe indirect arguments. So let's focus on quantizing these conserved charges here and just evaluating them and seeing do they obey the right algebra. I'll leave much of that as an exercise because at a certain point you'll see how it works. Okay, let's recall the stress energy tensor, energy momentum tensor. This is classical still. And we have this nice formula for it in the case of the Klein-Gordon field. So that's the expression for the conserved charges with respect to translations. And it's these guys that we're going to try and quantize today. We're going to put the hat on. Sorry, these are not the conserved charges, these are the conserved currents. We only get a conserved charge when we integrate it over space. The naught component over space. So the conserved charge for the translation x mu goes to x mu plus some a 0, 0, 0. Well, this one, we know what this one is, right? To translate in time, the conserved charge is the Hamiltonian. And we very happily quantized that one already. We didn't encounter any problems so far. So you put the hats on and it all worked out. It's just our quantum Hamiltonian that we wrote down at the beginning. I'll put a star next to it. I won't put a star next to it. I already defined h hat kg. So that was easy. Let's hope that the other three go as smoothly. So the other three are the generators of translations in space. We need an expression for these guys. Now classically we know what it is. It's just the integral of T naught j over all space. And we have an expression for that. It's phi dot dj phi. And in terms of the Hamiltonian variables, This is pi dj phi. Okie doke. It's nothing but the momentum operator, right? Total momentum for the field. Let's quantize this. By putting hats on in the naivest possible way. So you should be going, hang on. Wasn't there something about hats and pies and phis from the last lecture? Didn't I write down an example of a classical operator where the order did kind of matter? Well, indeed I did. There's more than one way to do this, but I've just written down the way that works. Save you the bother of trying lots of different ways. And, you know, I was going to do it, but I just think these are such good exercises. It's just substituting and differentiating. We're going to express these in terms of our ladder operators, AP. And there's this rather general picture that you get, and it's this. Oh, and there's 2 pi's, always the 2 pi's. So if you substitute in for phi, we know what phi is in terms of the ladder variables, and we know what pi is in terms of the ladder variables. Those expressions came from last lecture. It's a simple matter of substituting in for pi in terms of A and phi in terms of A, doing this derivative here, and then there's some cancellations that occur, and you end up pretty quickly with that expression. And now we are in the good position that these operators obey the right algebra. If you remember the propaganda of quantization, Poisson brackets get turned into commutators with an I, right? I wanted Poisson brackets. When you put the hats on, then this should the quantized hatted conserved charges ought to obey these canonical commutation relations here. This is the propaganda of quantization. Wherever you see a Poisson bracket on the classical variables, then the corresponding quantization has to obey this relation like this. And so we can check for the 4 conserved charges that we've now quantized, do they obey the right Poisson bracket relations? So does our 4 vector of H hat and Pj obey correct algebra is the question. And what is the correct algebra? Well, P to the mu, P to the nu. Does anyone know what the Poisson bracket between P to the mu and P to the nu is? If I translate this direction and translate that direction, 0. That's right. They're independent. They generate independent subgroups. They commute. Do the quantum versions commute? Let's find out. Well, this is a case of substitute and check. The Pj's, all expressed in terms of these AP, dagger APs. These are number operators. Number operators commute with each other, so they certainly commute with each other. And H, I don't know if you remember H. Is it still on the board? No, it is not. H was this exactly the same expression, but with a pi p. So these number operators always commute with each other, and hence we're done. So indeed, we have managed to produce a little part of the Poincare group already. We've produced the generators of all the space-time translations. We've got a quantum version. So that's a success, right? You should be happy about that. It's a good day's work there. But we haven't quite done it. I mean, what I'd like to do is to actually explicitly produce this projective unitary representation. That means we need a Hilbert space. So remember, unitary rep is the same as finding a Hilbert space upon which these operators act as generators of unitaries. And that's what we're going to do for the rest of today, is to produce this Hilbert space. And then just leave all the other part of the Poincare group alone. We'll deal with that later. It's a lot of calculations. So in writing down ladder operators, I've more or less taken for granted that you remember how to build Hilbert spaces with ladder operators. But let's now stop taking that for granted and actually produce the Hilbert space upon which all these operators act in the right way to give us a unitary representation. Thank you. And the Hilbert space we're going to build is, since there's ladder operators, A's and A daggers, then we know that the kind of Hilbert space that we're going to encounter is that of Fock space, right? So we commence our study with a highest weight vector in the language of representation theory, omega, that's annihilated by all these ladder operators. And our Hilbert space is found by just acting on this vacuum state with all the dagger operators, the creation operators. So the standard story goes that to build a Hilbert space with ladder operators is you start with your highest weight vector, the vacuum state omega, and then you start applying these dagger operators to build new states. And these states here we think of as a basis for a Hilbert space by just taking all finite linear combinations of them. That's not yet a Hilbert space, that's a pre-Hilbert space. You need to complete it with respect to the norm induced by the inner product. However, it's here that we encounter some technical difficulties, well, even a bit before, at the scalar product point. Because what we've produced here, if you think of the harmonic oscillator, you build these states by applying the ladder operator to the ground state, and you create Fock states, states with 1 photon, 2 photons, 3 quanta. And their inner products are pretty easy to work out, right? There's these 1 on n factorials, if you remember. But here we have another wrinkle, right? Because the commutation relations between AQ and AP dagger is a delta function. So these things here are not normalizable states. These guys are improper vectors. They're not normalizable, so we can't do this yet. You can't complete with respect to a norm if that norm evaluates to infinity on every 0 or infinity. Well, you can. It's just a very coarse Hilbert space, a coarse topology. So we're going to have to deal with this technical difficulty here eventually. But actually, we've seen this difficulty before in non-relativistic quantum mechanics. So if you take a look at something like lectures 9 and 10 of the Advanced Quantum Theory lecture of last semester, then you'll see that we built Fock space in that course, and we also built quantum field operators, non-relativistic quantum fields, and we talked about these improper states and how to deal with them. And the way to deal with them is you smear them out a bit, and then they become valid. They should become vectors in our Hilbert space. So that's the way to deal with improper vectors, is you smear them out. Because this represents, of course, n particles, each with a delta function, wave function in momentum space, localized at these momenta variables there, which is not a physical state. We're taught you can never prepare these vectors in the lab. So the way to produce real physical states is you always smear out these idealized improper vectors by creating vectors like this. And indeed, there's a way to rigorously build quantum field theory by taking the approach that quantum fields are those objects which eat smooth functions and produce for you correlation functions. I won't talk about that in this course, maybe towards the end. It's a very challenging way to axiomatize quantum field theory, but it does work in the few cases that it works. So honest physical states must always be smeared out, and then you can work with these guys. Oh, psi p. So there is a Hilbert space lurking here. It's just not generated by these, but smeared out versions of these. But there's a problem with this. The smearing process is not obviously Lorentz invariant. I mean, if you start breaking Lorentz invariants in your descriptions, then you have two things that you can do, right? You can either allow Lorentz invariants to be manifestly broken in the sense that you can't see it anymore, obviously, and then at the end you have to prove that it's there. Or the other alternative is to always force yourself to work in a way where the Lorentz invariance of your quantities is manifest, it's clear at every step. And then you don't have to prove anything at the end. But that means you have to do the hard work all the way through, or you can sort of put it off to tomorrow and then do the hard work all at the end. So both options are open to you. if you enjoy procrastinating, then you probably like the option of leaving the proof of Lorentz invariance right to the end. But if you like to get your homework and tidying your room done today, then it's probably better, I see people shaking their heads, it's probably better to keep Lorentz invariance manifest all the way through. So, well, what can I say? I guess in this course we're going to try and subscribe to the Keep Your Room Tidy school of thought, and we'll try and work with Lorentz invariant quantities the whole way through. So the difficulty really comes from the normalization of the single particle state P. I would argue it comes from that, right? I know P is not a normalizable state. So there it is. That's P, this improper vector. It has this inner product with Q. Now, is this Lorentz invariant? Well, not really, right? If I go to another reference frame, then this 3 vector gets transformed by the Lorentz transformation, and it's going to be some other thing, and it'll have some factor here, probably. So what we would like to do is we're free to multiply the wave function for this single particle vector by whatever we want, so that we can come up with a parametrization which is Lorentz invariant, so that someone in a different reference frame would write down a description of the single particle state which would agree. Because at the moment, if I say, okay, our particle is in this idealized state P, and then you're moving relative to me, well, you would say it's in another idealized state, lambda P, and then we would have a little argument about what's the normalization in front of this improper vector here. So I'm going to show you a neat way to normalize these improper vectors to build a new set of improper vectors that is manifestly Lorentz invariant, meaning that in a different reference frame you'd write down the exact same description of the vector as someone in a stationary rest frame. And then you have this nice clean parametrization, and then lots of the manipulations get easier. Let's find something now that everyone can agree on, no matter what reference frame they're in. So this is a projector. I've written it as a 1. I suppose that's stupid. But P is kind of a stupid letter as well. I'll stick with 1. 1 on the single particle sector. So the Hilbert space spanned by all single particle vectors is a subspace. And regardless of which reference frame I'm in, I'm going to agree that we either have a vector in that subspace or not. The actual wave function changes depending on which reference frame you're in, the exact wave function used to describe the state. But whether you have a single particle or not is an invariant concept. No matter which reference frame you go to, you'll always say there is exactly one particle in the system, which is the universe. So that's an invariant thing. And that's where we will start our discussion. However, this thing is not invariant. And this thing, therefore, must not be invariant separately. So separately, this integral here is not invariant under Lorentz transformations. This measure, this density here, changes depending on which reference frame you're in, as does this projector there. So the trick is to just change the sum around to find a coordinate, a different set of coordinates where both these two things are invariant. So we're going to take a factor, let's call this mystery factor x here, and a factor that this mystery factor x depends on p, and we're going to multiply by the mystery factor x up there. Mystery factor x. Where do we get mystery factor x from? See, I've just multiplied by 1 here, right? I've multiplied by mystery factor x on top and bottom. So the claim is that xp equals 2 omega p on 2 pi to the 3 is in fact our mystery factor. And we can prove this. So integral d3p is not invariant under Lorentz transformations, but integral d4p is. And that's kind of a neat little calculation that I guess I will do. Or not, depending on time. Wait on. So let's do a Lorentz transformation. I won't do that. That's mu, nu, mu, mu. So if you do a Poincaré transformation, change variables to p prime, then the Jacobian is lambda mu nu. And det lambda equals plus minus 1. That is an exercise. I'm not going to do that for you. So we've just shown that that integral measure is invariant under Poincaré transformations. Now, I guess the thing about this proof is there's a trick, and I guess in general you should prefer proofs that don't have tricks, but this one does. But I don't know an elegant proof that doesn't have a trick. So if you notice, the energy momentum 4 vector is invariant. The length of the energy momentum 4 vector is independent of reference frame. And it turns out this already has the seeds of the answer already in it. Well, what does that mean? The length of the energy momentum 4 vector, the energy momentum 4 vector, its length, its 4 length is invariant. And another way of writing that is by saying that p naught squared equals omega p squared. So now we at least see where omega p may enter the story. And if you solve this relation here for p naught, you're going to get two solutions. You'll get the plus square root and the negative square root. But the information of which branch you're on, either on the negative solution or the positive solution, that's a Lorentz invariant concept. It doesn't change under Lorentz transformations, at least not all through Cronus Lorentz transformations. So, if you restrict to, say, the positive branch, then that's a Lorentz invariant quantity. And we can restrict to the positive branch by adding in a delta function here. So this combination here is Lorentz invariant, just argued. So delta blah, blah, blah just tells us that we're on the upper branch. And being on the upper branch is a Lorentz invariant concept. This is a Lorentz invariant measure. Therefore, this number doesn't depend on which reference frame we're in. Therefore, neither does that. And so we've now identified mystery factor x. It's indeed omega p, the dispersion relation for a relativistic particle. So the notation is a bit treacherous here. Remember, these guys were called P underline ket. And with no underline, we mean this renormalized object there. And then accordingly, the normalization of these de-underlined objects. Sorry about the 2 pi over 3. It's just this. We'll get there in the end. Okay, square root of 2 omega p AP dagger vacuum. So these are just a scalar factor different from our original p underlines, but this is much more useful way to parameterize single vector states because they this parameterization is now an invariant concept. If you were in a different reference frame, then you would write down exactly the same vector as in the rest frame. Good. Now what we're going to do is finally express our operators in terms of this Fock vector space that we're going to build on top of these guys here. So we built these operators here, but we still don't know how they look on our Hilbert space that we're going to build in terms of these improper vectors here. What do they do? What's their action? Well, to work that out, we need a lemma we need to work out the commutator of the Hamiltonian with the ladder operators, and also the momentum operator with these ladder operators here. Now, without looking, I believe it has to be that. Yep. So the proof is left as an exercise because that really is one line. And similarly, the action of the commutator with respect to the momentum operator, if you go ahead and work that out, well, it's what you think it should be as well, namely that. And this delivers us the following corollary. And of course, that's just immediate from the line before. Well, it follows from the fact that P mu on the vacuum is 0. So not only do we now know what P mu, these generators of space-time translations, look like in a Hilbert space, we know much more. We know they're diagonal in this basis. So this basis diagonalizes these operators. It's as easy as can be. All right, that's, I think, what I wanted to say on that stuff. Now let's finally start talking about Lorentz invariance in terms of the Heisenberg picture, and then we'll be finished for today. So this allows us, in the Schrödinger picture, to quantumly implement translations. So we've built a nice unitary representation of the translation part of the Poincare group. For every 4-vector A, if we want to translate by A, then we build this Hermitian object A mu P mu. We exponentiate that. That's guaranteed to be unitary, at least at the level of rigor in this course. And that's our unitary translation. But that's in the Schrödinger picture. We should attempt to study things in the Heisenberg picture too, just in case it makes manifest some symmetries that were not clear to see or easy to see in the Schrödinger picture. And that's what we're going to do now. Of course, it's absolutely equivalent. But it will turn out to be very useful to think in terms of the Heisenberg picture when needed. Here it is. It's a Heisenberg picture, definition of an operator. Here's the original Schrödinger operator at some time. And of course, this is just the same as saying that dOH dt is I times the commutator of H with OH. Now, the Heisenberg picture becomes especially useful when we do perturbation theory for quantum fields later on. That's one reason why it's worth doing what we're about to do. Okay, I'm going to drop the h because I don't like writing h all the time. Basically, whenever you have a time argument explicitly put in here, you know you're in the Heisenberg picture. That much is easy. But what we're really interested in is how does phi change with time? Another reason why you might want to think of terms in the Heisenberg picture is that it makes real space calculations much easier to do. In the Schrödinger picture, it's, if you want to do a real space computation in the Schrödinger picture, it's not a pleasant thing at all to do. And so, which is unfortunate, right? Because we're not good at thinking in terms of Fourier transforms. Well, I don't know. If you have some practice, it gets easier. But describing spatially local processes is very difficult in the Fourier picture because everything's sort of delocalized and it's disgusting. But in the Heisenberg picture, it turns out that it's very easy to describe spatially local processes because this field operator here is defined at a point in space-time. And so it's very much worthwhile when you want to describe something occurring at a given space-time location to do it in the Heisenberg picture, rather than Fourier transforming everything. So these next calculations, what they're meant to do is meant to just give you the equations of motion for these operators in the Heisenberg picture, these spatially local operators. Of course, they're exactly the same as these equations here. We've already solved them, but we're just going to do the actual solution. And it's kind of a nice sanity check that you can work with these improper operators. Okay, so we've got to compute the commutative h with phi. We know phi, h is expressed in terms of phi's and pi's. Let's do that as the next step here. There it is. Big old commutator. There's a factor of 2 I forgot. There. Now, luckily, most of these terms just vanish because phi commutes with phi. So that's gone, that's gone. We only have to worry about one term, which is pi with phi. And the Leibniz rule for the commutator gives us a delta function, and it's actually quickly done. We end up with one missing line, pi tx. What about the equation of motion for pi? Well, this should remind you very much of Hamilton's equations, right? The change in the canonical position variable should be equal to the momentum. The change in the canonical momentum variable should be equal to the, we'll work it out. Same story. I'm not going to write out the full Hamiltonian, I'll just do this cheating notation. Now we're not so lucky. This first term vanishes, that's fine, but we have to do a commutator with pi and phi. Okay, that term is okay. But this one here is a bit annoying. We're going to have some delta functions. And we've got to be a bit more careful. We're even going to get derivatives of delta functions. Right, because the commutator of phi with pi is a delta function, but we still got this delta, this nabla acting on it. So that's what's going on here, and we get that 2 times. But whenever you see the derivative of a delta function, you should think integrate by parts, and then that puts that over to here. And so the next line is actually super nice. Is that, which is the Klein-Gordon equation. So now we know that the first derivative of phi gives you a pi, and the second derivative of phi gives you this. So let's combine that together. So a good sign indeed. So we get that this field operator obeys the Klein-Gordon equation. All right, that's what I have for today. So we're a bit closer to our goal of accepting that this is a relativistic quantum field theory. We at least know that it generates, that we get a unitary representation of space-time translations. About rotations, we will learn about that presently. We also get spatial rotations are unitarily represented. The only bit that's really missing is how are boosts represented. It turns out they indeed have a unitary representation as well by putting on hats. But this is the content of future lectures. We're going to build up to this slightly indirectly. In the next lecture, we're going to try and study the consequences of this observation here on correlation functions. And we'll argue that the theory is causal, respects causality, just by already noticing this observation here. And then only later will we actually get to the rest of the Poincare group. But I think as an equation to end on, this one expresses the Lorentz invariance of the theory most clearly, and we just got to work out how to extract these other representations before we'll finally accept that this theory is a true relativistic quantum field theory. But I think this is a good moment to stop, so I thank you very much.